Okay, in this video I'd like to introduce the topic of optical sources, and we'll deal with, in this topic, we'll deal with both LEDs and laser diodes. Actually, we'll also talk about optical amplifiers eventually, but in this video what I'll do is I'll focus on the LED. The LED and the laser diode are both used in fiber optic systems. The LED is a little bit simpler in its operation and certainly simpler in its response functions, so we'll start with that. Basically, an LED starts with a semiconductor which doesn't really conduct very well, but if we dope it with P and N doping centers, we can create conductive semiconductor. Okay, and in the P region we end up with holes, and in the N region we end up with electrons, and in each of these regions either the hole or the electron are more or less free to move around in response to an electric field, and so both of these parts of the semiconductor become conducting. However, if you create this heterojunction between the two different types of doping regions, then you can see that if you put a positive bias on it, that is, if you bias it in such a way that you're pushing the P's, the holes, over towards the electrons, and you're pushing the electrons over towards the holes, it will conduct. But if you reverse bias it, you will tend to push the holes and the electrons apart from one another, leaving what's called an intrinsic region in between, which is again acting like a semiconductor, not conducting well. And so if you put a positive bias on it, it conducts, and you put a negative bias on it and it does not conduct. That's the diode operation. That's what a diode does. It conducts in one direction but not the other. And so the LED is created in a semiconductor such that when we put the positive bias on it and cause current to flow, the holes and the electrons are combining, and when they combine, you can think of the electron falling into the hole. They give off a photon with an energy equal to the band gap. Okay, so positive bias gives us conduction, and it also gives us electron and hole recombination, or they recombine. When they recombine, photons are generated. With energy, Wg, where Wg is equal to the band gap energy. And in this class, although the book goes into some detail on semiconductor device physics, we're not going to spend a lot of time on it. We're going to say, look, we know that when we put the positive voltage across this PN junction, that we're going to get photons out, and they're going to have this energy. Okay? And so what we're going to do is we're going to say that, well, what we're interested in is the response curve. And we're interested in P optical is the output. And we're going to go ahead and say that the input is then going to be the current that we put into it. Okay, so, sorry. And it turns out that the response curve of an LED is really quite simple. We have, some slope here, and we're going to plot response versus the input current here, and the behavior is more or less linear. And what we can do is we can say that what we're going to do is we're going to say that each electron that's produced is converted into a photon with some efficiency, quantum efficiency eta. And this is the fraction of electrons in the flow that when they combine with a hole actually produce a photon. It doesn't. Every electron-hole recombination doesn't produce a photon. Okay, but some fraction of them do. So this is the fraction of electrons that produce a photon when recombining with a hole. Okay, and so then the question is, what is the energy of each well, we know that each electron, when it does convert into a photon, it has this energy of the band gap energy, and so that's going to be the energy of our photon. Okay, and so what I'll do is I'll go down here to the next page, LED, and I'll say that Wg is equal to the photon energy. And we know from our earlier chapter that the photon energy is equal to hf, where h is Boltzmann's constant and f is the frequency. And if we write the frequency as c by lambda, then we can write the wavelength of the output as hc over Wg. Okay, so this is the first equation that we have that tells us the wavelength of the output as a function of the material property. So Wg is a material property. In other words, different materials are going to give us different wavelength of output, and so we're going to have, depending upon the manufacturability of these materials or of these heterojunctions and of the processing capabilities of different materials, we'll find certain materials are much more cost effective to work with, and therefore we're ending up with certain wavelengths depending upon those materials. Okay, and now what I can do is I can say that let's see here, if we want our optical power out, the optical power is going to equal the energy per unit time, right? And so that will equal the number of electrons per unit time, per second, times the efficiency with which they're converted into photons, times the energy of one electron. So this is the electrons per second. This is photons per electron, and this is energy per electron. And let's see, we have energy per unit second then. Well, this is just the efficiency of the whole process. There we go. Now we have energy per unit time here. Okay, and so yeah, eta is a unitless quantity. It's an efficiency. So we end up with energy per unit time, which is power as desired. And now let's see, we can rewrite the input current as charge per second, and charge per second is charge per electron Q times electrons per second N. Okay, so this is Q is charge per electron, and this is, again, electrons per second. Okay, so finally we can put all these together, and hopefully writing it out like this. You don't usually see it written out like this in the text, but this is the way that I can show it most clearly, I believe. And so finally the optical power is going to equal, let's see, N is I over Q, eta, and WG. So this is essentially the next equation given in the book. Well, just a second here. The charge per electron, we're supposed to be writing that as an E. Sorry. Okay, so this is the equation in the book, and we can rewrite this as WG eta over E times I. And this is written, at least in your homework assignment, on the equation I gave there, as delta P over delta I times I. So this is more or less a constant. And so this, going back here to this curve, this is that slope, WP over I, or WG eta over E. Okay? It turns out in real LEDs, we're generally, you can't increase the input current forever and still get more and more optical output. At some point, it saturates. And so in the real device, instead of going like that, we have some saturating optical power. Okay, and this would, maybe I'll call this P max here. Okay, so this is what the response function of the LED looks like. And we can derive the slope from it based upon the semiconductor operation. As I say, without going into too much device physics, sort of just believing that the photon energy is going to be that band gap energy of our semiconductor. Okay, and a semiconductor is defined in terms of its band gap energy. Okay, I will continue with the next video talking about the sinusoidal input to the LED and what the output looks like. Thanks.